Hello everybody and welcome to our talk on privacy-preserving public key infrastructure for vehicular networks, which is based on a paper authored by Kumar Ranjan, Thomas Basmer, Florian George, and me, Pablo Gajduk. In the next 15 minutes, I'll talk about our motivation, present to you the original design of the public key infrastructure for intelligent transportation systems, talk about our proposal to improve it with regard to the privacy, and finish off with a discussion of the feasibility of our approach. Let's dive right in. The Cooperative Intelligent Transportation System, short CITS, is a concept of all traffic participants exchanging information with each other and the infrastructure. It is done to get a better and a more holistic view of the situation on the road. Its introduction has many goals, among others, to increase the road safety, to reduce the effect on the environment, and to increase the efficiency through reduction of congestions. In this next slide, you can see a picture of a typical ITS. Vehicles are communicating to vehicles, to pedestrians, to the infrastructure. This is all can be called vehicle-to-everything communication, or short V2X. One of the important means of the vehicle-to-everything communication are so-called cooperative awareness messages. Those are being distributed by vehicles approximately every second. And they contain information such as vehicle's position, the direction of movement, and so on, so that even traffic participants that cannot see the vehicle can still receive this information and plan accordingly. On one hand, the information contained in CAMs is safety relevant for other traffic participants, so the vehicles need to be held accountable for the correctness of the information they provide. On the other hand, this information is of private nature, since, for example, it contains the GPS position of the vehicle. Therefore, the CAMs themselves need to be unlinkable to the identity of the vehicle that sent them. For this reason, it was decided that the CAMs should be signed with a pseudo certificate, which is distributed by a public key infrastructure to each vehicle. In the following slide, you can see the architecture of a Pilot-PKI as it is proposed by the European Telecommunication Standardization Institute. It contains of root CA, which is providing certificates to all the others authorities. There is the original equipment manufacturer, which manufactures the car, and during the manufacturing process, it is writing its canonical credentials into the car. The canonical credentials contain the real car's identity. Now, to obtain pseudo certificates, the car needs to first send its canonical credentials to the enrollment authority. The enrollment authority verifies the canonical credentials. It can also contact the OEM in case it's needed. And then it provides the enrollment credentials to the car. Enrollment credentials, however, are pseudonymized and signed by the enrollment authority. In the third and last step, the car sends the enrollment credentials to the authorization authority. The authorization authority verifies the signature of the enrollment credentials and sends the ATs, the pseudonymized tickets, to the car. Those tickets are the pseudonymized certificates used to sign the CAM messages. According to the standard, the identity of the vehicle is protected by a concept of separation of concerns, since only the enrollment authority knows the real identity of the vehicle and the authorization authority only sees the pseudonymized enrollment credentials. However, if those two authorities collude and exchange too much information with each other, the real vehicle's identity can be linked to its pseudonym. In our work, we propose to use authentication with zero-knowledge proofs. Zero-knowledge proofs are a cryptographic concept of proving the knowledge of some secret to the other party without disclosing this secret. Consider the following example. Two parties, the prover and the verifier, are playing Where is Waldo? The prover has found Waldo and now is wanting to show that he knows where Waldo is to the verifier without actually showing where Waldo is. For this matter, he takes a large piece of paper, much larger than the picture with the Waldo, and makes a hole in it, a little small hole. Now he places this paper over the picture with Waldo so that the verifier doesn't know where the picture is Waldo exactly is located. so that the Waldo is visible through this small hole. The same way in our case, the vehicle will be able to show the possession of the canonical credentials to the authority without disclosing its identity, which is embedded in the canonical credentials. It will also be able to prove the correctness of the signature provided by the original equipment manufacturer. It is to be noted that in our work we use a more modern zero-knowledge proofs called Ziggy snarks. Those are short, non-interactive zero-knowledge proofs with a constant verification time. However, the construction of the proofs is still very computationally intensive. It puts a huge load on the CPU and RAM. The usage of zero-knowledge proofs allows us to simplify the architecture. Now we have only one single authority instead of two. So to get the pseudonymous certificates in our case, the vehicle needs to prove to the single authority with a zero-knowledge proof that it has received a canonical credential from the OEM with its identity. It does it without disclosing its identity. It proves that the secret included in the canonical credentials as well as the signature from the OEM are correct. The fact that the Ziggy snarks are short and can be verified in a small, constant period of time brings us several advantages. First of all, we reduce communication due to use of single authority and the payload is getting shorter. And second of all, we better protect the authorities against DDoS attacks since the computation load is much higher on the car side than the verification on the authority side. However, the inability of the authority to track the certificate back to its owner poses a threat to the accountability. The IDS standard assumes passive revocation. That means that the authority can issue certificates with a short validity period, and if a misbehaving vehicle is out of certificates and will come back to the authority for more certificates, its request will be simply rejected. However, in our case, since the authority doesn't know and never gets to know the identity of the vehicle, this concept doesn't work. To solve this issue, we have adapted the fast, anonymous, reputation-based blacklisting scheme from a paper by Xi and Feng to our needs. This FARP scheme allows one to do the following. It introduces the concept of reputation to each vehicle, and the CAM messages that the vehicle distributes will be judged by other traffic participants, and the scores are going to be submitted to the authority. Prior to requesting new certificates, each vehicle will need to redeem its previous score from the authorities. For that, it will need to authenticate itself using zero-knowledge proofs, get the scores, and add those scores to its current reputation value. After that, while requesting new certificates, it will not only need to prove that it has the right canonical credentials, it will also have to prove that its reputation, together with the redeemed certificates, is higher than a certain threshold. This explanation, however, has been greatly simplified. For further details on this scheme, please consult our paper. In addition to the design, we have also developed a software client for the vehicle side of this communication, and we have measured its performance on the onboard communication unit, short OCU. The performance measurements were done for two procedures, authentication procedure and the redeem procedures, with several ZK zero-knowledge libraries like gsnark and Socrates, and also using different hardware setups and different calculation methods. As you can see from the diagrams on the slide, we were able to get down the computation time for authentication procedure to 74 seconds and for the redeem procedure to approximately 67 seconds. This is still quite a long time for one procedure, so we decided to also repeat the same measurements on the regular consumer laptop. Due to a better CPU and higher RAM capabilities, the same procedures took only approximately 5 seconds on a consumer laptop. According to a regulation document called Delegated Act on V2X, the maximum anonymity a vehicle have to utilize at least 15 certificates every day. That makes a vehicle redeem 15 certificates from the previous day each day, and also if it doesn't want to request the certificates in a bundle of 15 certificates, Then it has to make 15 requests, so that means 15 authentication procedures every day. This brings the total time spent by each vehicle computing zero-knowledge proofs to 35.5 minutes. Well, we still think it's feasible for electrical vehicles while they're being charged in the garage overnight. For the transition phase of the ITS, it might be possible as well to outsource these computations to the consumer laptop of the owner, for example. For this, the vehicle only needs a stable Wi-Fi connection to the laptop, and the computation will be done on the laptop while the vehicle will do all the communication with the authorities. This concludes our presentation, and I would like to thank you all for your attention. These are the sources used by me in this presentation. Thank you.